Hi, we are in chapter 3. We're past that chapter 2 with all that counting. So that just, again, that's a tough section for some people, especially if it's new. So from here on out, I always feel very comfortable because this to me is probability. And not that counting isn't, I mean, you need counting, but don't be discouraged. That to me is tough, especially if you've never seen it before. So here we are now. We are in chapter 3, and we'll be there a couple days. And you know a lot of probabilities now, like probability of A, probability of the union, like A union B. Um, we've talked about probability of A intersect B. We have a nice theorem for how to find this. In section 3.2, we talk about a nice property for finding probability A and B. Conditional probability, what you're trying to do is find the probability that some event occurs given. So for us, this means given another event has already occurred. So what's the likelihood A happens given you know B has already happened? Um, Again, like what's the probability, a tree is down in your yard given you had a really bad storm. Knowing you had a really bad storm probably makes the probability that you have a tree down much more likely. So sometimes when we're given an event, it makes the other event perhaps more or less likely to happen. If it doesn't, then actually we say those events are independent. So that's what chapter 3 is doing. And again, a nice comic. I mean, after you take probability, you can't help but think about gambling. Well, just chances all the time. What's the chance of this, chance of that? I don't know. I just do it all day long. So if you've never been to Vegas, it's interesting. I'll just say that. Probably shouldn't say any more. So 3.1 is about conditional probability. And what I mean there is you have some partial information, you have some condition, and then you have to determine a probability, maybe more or less, given that condition has happened. So I'm just going to I'll just do this example. What's the probability of getting a face card in blackjack, or 21, given that you're playing with one deck of cards and no cards have been dealt? It's pretty likely, you're going to get a face card. If no cards have been dealt on one deck of cards, it's going to happen. But let's say you're sitting at a blackjack table. Let's go back to a casino now. Don't worry about it. You're sitting. All you know is that you're playing with one deck of cards and you've already seen 10 cards that are face cards. What's the probability the next card you're going to get is a face card? If you've already seen 10 face cards out of a deck, the likelihood of getting a face card next is not as likely as it was in question 1. Oh, Dr. Rickard is writing to me. I shouldn't do another one, but again, what's the probability of getting a new car loan? You might think right now you have a good opportunity. If later you find out I owe $50,000 on my Discover card, I think you're going to realize this probability almost becomes 0. So the notation we just have to clear up. I know in different fields this little line means different things, but in probability this means A given B. And this is the formal definition of it. I mean, you already know what probability A and B, this is the intersection, and this is just probability of B. So I think this picture helps me a lot. The probability that A happens given B has happened. When you know B has happened, you know you're sitting in B. Now, the only way A could possibly happen is if you're sitting in the intersection. So it makes sense that you're really reducing your sample space to B, and then you're finding the likelihood of the intersection over B. And so if these guys are mutually exclusive, actually, probability of A given B is, and this, if I knew how to use the software better, give a pause. If A and B are mutually exclusive, let me draw you a little picture. Here's A and here's B. If B has occurred, what's the probability A is going to happen? Darn, I'm going to have to learn how to use the little stop and answer thing, but it's 0, right? If B has happened, there's no way A is going to happen if they're mutually exclusive. This is just a short example of rolling a 6-sided die, and yeah, A is the probability of getting, let me see, A is the event of getting a 2, and B is the event of rolling an even. So the sample space is 1 through 6. A is the event 2, B is the event even. Probability of A, probability of B. Now what I want to find is the probability A given B. So if I roll the dice and I know that B has occurred, so let me just say I'm playing dice, I don't know, I just know I rolled it and somebody said, oh, it's an even. I hear them say, you have an even. The probability now that I have event A 2 given even, is just 1 out of 3. So notice that before probability of A was 1/6, and now probability A given B is 1/3. B, conditioning on B, changed that probability. And in fact, I can say the word now, A and B are dependent because B is affecting A's probability. If they're independent, B would not be affecting it like that. Probability of B given A. What's the probability that you have an even given you know you got a 2? So I roll a die and somebody says in the back, oh, you got a 2. And I know B has occurred, and that's just 1. It certainly has occurred. I can make a rule. It wouldn't be new. I'm not presenting anything, but if A is a subset of B and A has occurred, then B is 1. It's going to happen. So I just put a couple examples. This is a nice, just a small example there. Let me go down. The next page is a bunch of examples. Yeah, this is just the actual day forecast and what actually, I guess here's the forecast and here's how the day actually turned out. What proportion of days was sunny, actually sunny. So if I add across here, this is where I'm getting 40%. Okay, and notice this whole, if I add across sunny, cloudy, rainy, they're mutually exclusive. It'll add up to 1. Same way down here. Proportion, yeah, wrong. Wrong just means whatever they, wrong would mean, right, this is right, this is right, this is right, in the sense that this was the forecast and this is what actually happened. So these were all the right calls, and the wrong calls would be everything else. So this is 60%, is that right? No, I'm lying. 70%. So probability of being wrong is 30%. In Terre Haute, I think it's a lot more than that, but that's not my problem. Well, that's not the discussion. So here's what I mean by conditioning. Given the forecast was sunny, if the forecast is sunny, you know you're sitting right here. You're sitting in sunny. This is your new denominator of your sample space. So what is this, 44? Yeah, here's 0.44. What's the probability? So given it was sunny, what's the probability of rain? So this is rain over sunny. And that's where I'm getting 0.01. It's just that intersection over the whole sample space. Oh, okay. That's the only conditional. I guess I asked some other things. Oh, these are just some rules. This is just saying that probability of A given B is a legal probability. It follows all those axioms that we talked about earlier in the quarter. So that's all that's saying. And here's a couple, I mean, we've pretty much been doing this. When you do conditioning, one easy way, if you can kind of picture the sample space, is reduce it and figure out where you are and then compute the probability you're asked for. So suppose 2 fair dice are tossed and the sum of their top faces is divisible by 5. If they're divisible by 5, it has to be one of these, right? So 1, 2, 3, 4, 5, 6, 7. What's the probability that both of them landed on a 5? Well, I'm reduced to everything to divisible 5. I'm only down to 7 things, and this is the only one that are both 5s. So that's where that's coming from. Again, down in this problem right here, I'm just reducing sample space. The guy's already seen so many movies, so I can just boot them off the list and act as if they don't exist anymore. I mean, I'm reducing to what I'm currently at. And why I put these two together, because this isn't, I don't think 3-2 is a big stretch. If you believe this definition, probably A given B is this, which I think it makes nice sense. You know that we have a rule for probability of A or B, right? We've been doing this as probability of A plus probability of B minus probability of A and B. But we really haven't given a definition yet for probability A and B. And most people naturally think, oh, then you just multiply them. Well, this is true, but you have to have, this is true if A and B are independent. And if they're not independent, this doesn't hold. So I have to be very careful. So to get a true definition for this, just do a little cross multiplying. And you can see right here, this is how we define A and B. It's a probability of A conditioned on if A has happened, then it's a probability B conditioned on A has happened. And I think these examples kind of, I mean, you naturally do this, you just don't think about you do this. My dog, she was on my bed just a minute ago, but probability she would detect an intruder is 0.8. The probability that she actually scares the intruder, given she detects him, is 0.9. What's the probability she detects and scares? So what's the probability she detects and scares the intruder? Well, that's the probability that she even detects it times the probability that she scares given detects. I mean, I guess that I could also look at the probability she doesn't detect it times the probability of scaring given don't detect. If she doesn't detect, this probably is 0. The probability she scares, if she doesn't detect the intruder and they don't detect her, this probably becomes 0. But so what I'm saying is I'm just multiplying these two things together, but I'm conditioning. I think you naturally do it and you don't think of it. When I want to find the probability A and B and C, I'm always thinking about what happened previously. So this was just, I don't know, I guess I only have so much time, but I mean, we can extend this to many, many events. And I wish I had one where, I guess all of these are kind of true. Well, they're all true, but um, I feel like, yeah, this is just very long, isn't it? But I'll leave this. I mean, I hope that makes sense. I think again that you're naturally conditioning, even though a lot of us don't. Let me say. Here's a good idea. What if I want? Right now we have 25 people in the class, and I need to pick. Hmm. I need to pick. I don't know what the breakup of guys and girls is. Let's just say female in this class right now is 10 and male is 15. And let's say I can pick 3 students for a trip with me to Las Vegas, and I put all your names in a hat and pull you out. What's the probability I pick all females? And I'm not going to pick somebody 3 times in a row, so I'm picking without replacement. So the probability the first person I pick is female would be 10 over 25. Times, now I'm not going to put 10 over 25 here because I picked one female and this is down to 9. So conditioning that I already picked one female, this is 9 over 24. Okay, and that's what I'm saying. I mean, you naturally do this. I don't think you write out all these conditioning statements. You just think that way. And then the probability that the last one, now I'm down to 8, would be 8 over 23. So I hope that helps. And this is one of my favorite. I probably should have given this as a bonus. This is a great. I like this as a bonus, but you can read it. It's a nice little problem. I think most people think you should choose. They try to come up with all these crazy formulas, but it actually this problem. It doesn't matter where you are in a line. Um, I should get halfway into it, but it's a nice problem. Very nice little bonus. So okay, if I can remember how to stop this thing, and it will go up.